Okay, I'm just going to make this quick video talking about constructive and destructive interference and path difference a little bit more. We had this warm-up question where we have two speakers and they're playing an audio tone and the wavelength is given, and it wants to know what the listener at point Q would hear. And so this would be a question about whether or not there's constructive interference or destructive interference. And if there's constructive interference, a listener at Q would hear a louder tone, and if there's destructive interference, they would hear either no tone or it would be a very faint sound. And so the question is, how do you go after problems like this? So just as a reminder, whether or not you have constructive or destructive interference only has to do with the path difference. And when I say path difference, what I mean is some waves are longer than other waves. Some waves have farther to travel. And we had looked at this slide here, and in this example, you can tell looking at wave A and wave B, you can tell that wave B has farther to travel than wave A, and so the path difference is the amount that wave B is longer than wave A by. It's this difference here. So this wave right here has a path difference, and if you look at that, you see a trough, and that is half of a wavelength. And if you look here, you have 1.5 wavelength path difference, 1 wavelength path difference, and let's see, 2 wavelength path difference. And so the idea is that when you have an integer number of wavelengths is equal to your path difference, let me write that. Let me actually write this just mathematically. So the condition for constructive interference is that the path difference is an integer number of wavelengths, and we write this like this, where n is an integer, 1, 2, 3, and so on. And the condition for destructive interference, going back to the picture, destructive interference is that the path difference is a half integer number of wavelengths, like this. So in the situation where the path difference between the two waves was half of a wavelength here and 1.5 wavelengths here, in that situation we have destructive interference, which you can tell just looking at these two pictures. We're going to have destructive interference there, destructive interference there. So when you have a problem like this, basically what it comes down to is, if you look at these two equations, if you look at the ratio of the path difference, to the wavelength, if this ratio is an integer, then you have constructive interference. If this ratio is not an integer, like if it's like 1.5 or 2.5 or 3.5, then you have destructive interference. And so the problem just comes down to trying to figure out what is the ratio of the path difference of the wave to the wavelength. Now, in the warm-up question, this is not too difficult. Let's actually take a look at this. So in this case, we have the wavelength given is 0.8 meters, and the path difference between speaker A and speaker B is 2 meters. Now you might say, how am I getting the path difference is 2 meters? Well, because if you look at speaker A is 3 meters from point Q, and speaker B is 1 meter from point Q. And so the wave that travels from B to Q has less distance to travel, and the wave that travels from speaker A to point Q has a longer distance to travel. How much of a longer distance? Well, 2 meters, because it's 2 meters behind speaker B. So that's why the path difference between A and B is 2 meters. And so if we look at that ratio, going back to our conditions for constructive and destructive interference, if we look at that ratio of path difference to wavelength, we get that ratio is 2 over 0.8. And if you calculate that, 2 divided by 0.8 is 2.5. And so we can see very clearly that is not an integer. That is a half integer. It's in between 2 and 3. And so that implies we're going to have destructive interference at Q, and therefore the sound at Q would be quiet or faint. Now I can go on to a different example. Let me look at a more complicated example. And first let me just point out this picture here. This is kind of the situation we have in the warm-up, only in the warm-up the separation between the two speakers is a little bit longer, but you see if speaker 2 is behind speaker 1 by a half integer number of wavelengths, then you get destructive interference. And so your wave would have 0 amplitude here. That's why you would have a soft sound at point Q in the warm-up above. And that's just another picture of the same thing. This example, I did it in one of the classes. I didn't do it in the other class. But this is a slightly more complicated example of the same type of situation. Let me clear off some space. And this problem says, suppose two in-phase loudspeakers, A and B, are separated by 3.2 meters. So I'm going to draw this out, actually. So I've got two loudspeakers, A and B, and they're separated by a distance of 3.2 meters. And it says a listener is stationed at point C, which is 2.4 meters in front of speaker B. So here's point C, and the separation is 2.4 meters. And the question says both speakers are playing identical 214 Hz tones, and the speed of sound is 343 meters per second. Is the sound heard by the listener loud or faint? So this is the same type of question. Now it's a little bit more work. Now we're not given the wavelength, but we're given the frequency is 214 Hz, and we're given the speed of sound and air is 343 meters per second. And if you remember the wave equation, then you realize that you can calculate the wavelength pretty easily. So the wavelength would be 343 divided by 214, and about 1.6 meters. So the question is, what do you do with that wavelength? Well, again, it all goes back to the path difference. You can obviously see that the wave coming from speaker A here has longer to go than the wave coming from speaker B to make it to point C. So what is this distance? Well, luckily we know that the Pythagorean theorem. We can find the distance from A to C using the Pythagorean theorem. That would just be the square root of 3.2 squared plus 2.4 squared. My pen's not working correctly. Square root. So that distance would be 3.2 squared. And so the distance from A to C would be 4 meters. So the path difference, the wave coming from speaker A has a longer path length, and so the path difference would just be 4 meters minus 2.4 meters. In other words, the wave coming from speaker A has to travel a longer distance. How much of a longer distance? 1.6 meters. And in this case, you don't even need to really look at the ratio, because you can tell immediately, hey, the wavelength is 1.6 meters, the path difference is 1.6 meters. That should be constructive interference. If you want to show it mathematically, you just say the ratio of the path difference to the wavelength, plug that into the calculator. Just kidding. It would be 1. And because that is an integer, you have constructive interference. So hopefully that helps explain, I don't know what's going on with my pen here. Hopefully that explains the concept of constructive and destructive interference and path difference a little bit more. Hope that helps.